Okay, so let us look at the second method. As I mentioned, the classical method can be applied only in a very restricted number of applications. Uh, but all those probabilities that we calculate using that method is actually exact probabilities under some assumptions. For example, fair die, fair coin. Rather than that, all the probabilities are exact probabilities. But more practical one is the relative frequency method, which gives you only an approximate probability most of the times. So let's look at just one or two examples. So this is just an A-level type problem. There are 50 students in a class, different types, for example, 26 boys, 24 girls, and then out of boys, 16 times mathematics, 12 times statistics, and so on, so on. Some information is given. Based on that, some probabilities have been asked to calculate. So in this case, actually, we are looking at only those 50 students. In that case also we get the correct probabilities. But as I mentioned, if you consider some experiment which can be repeated, if the events are coming from that kind of situation, then the probabilities that you get based on a large number of experiments will still be approximate probabilities. So let's look at this one. How do we usually, what we do in A-levels is to draw a Venn diagram for this kind of situation. Right, so there are 50 students, male and female, so that population can be divided completely into two parts, males and females. Right. And then among the boys, 18 like mathematics, 12 like statistics, and 6 like sports subjects. Right. So among boys, and then among girls also similarly 12 like mathematics, 13 like statistics, and 4 like both subjects. There can be some students who don't like any of these also. Based on this information, each student like either mathematics or statistics or both, or neither. No, neither. Using this data, find the probabilities that the randomly selected student has the following properties: likes mathematics or statistics, likes neither subject, and so on. So usually this kind of problems are easy to solve if you draw a Venn diagram like this. Right. So based on that, I will look at how many in each subset, and then based on that you can total test 50. So therefore you can get the probabilities. So 26 male and 20 female, and then out of that number of people for mathematics and number of people like statistics and so on, those information are given. Right, so based on that we can draw this Venn diagram, and the probabilities can be calculated. So what is the probability that randomly selected student likes mathematics or statistics? Mathematics or statistics means all to be right, all these. Right? So therefore we have to add all those 6 numbers here, divide by 50. Right. Likes neither subject. So that means this here, right? 5 divided by 50. So like that, that's how we calculate probability. What is the probability that a randomly selected student is a boy who likes only mathematics? Boy only math is this. So 12 divided by 50 and so on. So I think that's easy. And similarly, quite similar problem. In a large manufacturing facility, an opinion survey was conducted regarding 3 types of bonus schemes. A random sample of 960 employees were selected, and the job category and the bonus scheme of employees were recorded. So job category and the bonus scheme, right? So there are 3 bonus schemes, so everybody can select any bonus scheme. The results are given in the following table. Right? So this kind of table is called contingency table or 2A table. So this 4 by 3 contingency table. So based on this also we can calculate various probabilities. What is the probability if you randomly select an employee, what is the probability that he will be a laborer? That will be 630 divided by 960. What is the probability that if you randomly select one, he will be a clerk who has selected bonus scheme 1. Class selected bonus scheme 1 is number is 82, so 82 divided by 960 and so on. We calculate those probabilities. So those are just proportions, but we take them as the probabilities. Right. If you have this kind of problem, this is related to example 12.4. Example 12.4. So again you have some data. Right. You may have, in this case we have only a group frequency table, but sometimes you might have individual values also, right? The weight of milk powder bags is the variable considering here. So a certain production process, milk powder is filled into bags. A bag is called non-conforming bag if its weight is less than 398 grams or more than 403 grams, otherwise it is said to be conforming. So they have measured 500 bags, but we are not given the actual weights, we are given some frequency table here. Right. So based on that, these questions have been asked. The bag is randomly selected from the process. A is the event that the bag is a non-conforming bag. Non-conforming means less than 398 or more than 403. So less than 398 means this 10, more than 403 is 50, so altogether 25 divided by 500 if you want to find out the probability of A, that will be. Right. So that in this case actually this 500 is only a sample of the whole manufacturing facility, right? So if I ask the question, if you randomly select a bag from the manufacturing process, what will be the probability that the bag will be a non-conforming bag? We have to answer that based on this particular sample of 500. Right? So therefore there is an actual probability, but we are getting is based on this particular sample, that will only be an approximation to that probability. If you take another 500, my answer will be different. So at that point, relative frequency, whatever the relative frequency will be my answer. So, but the previous two situations we were considering a class of 50 students. So we are asking if we select a student from this class. So out of that 50, in that case our probabilities are exact probabilities. And similarly in the previous one, 960 employees, out of those employees if we select, it's a different situation. But here this sample of 500 is coming from a certain process. So there's a larger population, right? The question is not asking about, usually in this kind of situation we are not asking the question what is the probability that in the sample if you select this many it will be non-conforming. Usually we are interested in about the process. So therefore the question is usually about if you randomly select a bag from the process, what will be the probability that it will be non-conforming. So when you answer in that kind of questions, the probability that you get using the sample will be an approximate. Right, so what was the question? A bag is taken randomly from the process, what is the probability? So that answer, probability of A, right? is approximately equal to then those two numbers divided by 500. What is the probability that the weight of random selected bag will be more than 400? So I think we can get the more than 400 number in the sample also directly from that. So if you can get directly from the table, you can get that number divided by 500 will be approximately the probability. But sometimes in the last part is okay, more than 400. I think it's not 400 was not here. So in that case, you'll have to do a kind of a interpolation here. You have to make some assumption and calculate. Let's see. And more than 400 you can directly get, right? So more than 400 means over together all this 400. One might ask a question. More than 500. Exactly 400 is also included here. So how do you get more than 400? Will be asked sometimes. So if you want to be that accurate, somehow probably you will have to assume that okay, 400 means up to 400.5, less than that. So more than 400 is more than 400.5. So that number you will have to kind of get by dividing this interval 150 to this interval and then multiply by the length of whatever the interval we want, right? 405 to that part, right? So there will be a small adjustment in this case. But anyway, doing that kind of adjustments are not going to be important because whatever the probability that we are going to get, considering this exactly like this, also approximate. Right? These are approximate probabilities. So even if you try to be more accurate, it doesn't. It's not going to make that much difference for that 0.5 length. So knowing that these are approximate probabilities, you don't have to worry that much. Okay. So here's the question. 3 bags are taken randomly from the process. That is, event B is 1 bag is non-conform. So what is the probability of happening that? If you take 3 bags randomly from the process, right, from the process, not the sample. Right? What is the probability that 1 bag is non-conforming? That means, the question asks, if you take a random sample of 3 bags, what is the probability that 1 is non-conforming? That means 2 is conforming. What is the probability of happening that? How do you find out that? Any bag is non-conforming. Probability that any bag is non-conforming is 10 plus 15, right? So 25 divided by 500. That is the probability that any bag coming from the process is non-conforming. Therefore, any bag coming from the process is conforming is 1 minus that amount. 1 minus 25 divided by 5. So we know those two probabilities. So if you take any 3 bags, what is the probability that 1 bag is non-conforming? You have to look at all the possible ways of having 1 bag, and then you know that probability that any 1 bag is not conforming. Like that you can calculate. One way to calculate is actually this using probability rules. We will discuss that a little later. Probably when you are using the probability rules, we can use. Any other way to one bag is not conforming can happen like this: conforming, non-conforming, non-conforming. O, non-conforming, conforming, non-conforming. Second one is O, non-conforming, non-conforming, conforming. So if you define several events, for example, if you say event C1 is the event that the first bag is conforming. First bag is non-conforming can be written as C1 dash, right? You don't need 2 letters, you can write down. And similarly, if you define C2 to be the event that the second bag is conforming. Using the same event, you can say define the event second bag is not conforming by C2 dash. Similarly, C3 is the event that right. Let's define three events because we know the probability that any bag is conforming, and similarly we know the probability that any bag is non-conforming. So if you know that those probabilities, you know probability of C1 is equal to therefore 475 divided by 500. Right? This is the same probability of that. So we know those probabilities. So now what we want is to find out a certain event like conforming, one bag is non-conforming. So for example C1 dash, this one and C2 and C3. First one is non-conforming and second one is conforming and third one is conforming. O, first one is conforming and second one is non-conforming and third one is conforming. So one is non-conforming here. O, first one is conforming, second one is conforming and the third one is non-conforming. So this is the way of happening that particular event. So what we are interested in the probability of this. So this is where actually we need the probability roots.
So can you just multiply those three and
you cannot only multiply. Why multiply? You have to know. You have to have a reason for that. Why don't you multiply? Why don't you add?
I mean the above.
Right?
PC1, PC2 and PC.
Yeah. So yeah, you can say you know the probability rules. Actually, you are applying the probability rule here. That's what's happening. Now I will come to that little later. Now these are three events. For example, these say A1, A2, A3. So this can be considered this whole event. What we are interested in is actually A1 union A2 union A3. There is a probability rule saying that if you apply that probability rule, the probability of this whole thing should be equal to probability of this A1 plus probability of A2 plus probability of A3. They are plus, right? Because of some reason, we are coming to that later. But probability of A1 will be equal to probability of this times probability of this times probability of this because of another reason. Right? So that's why I said probability you have to know these things. If you know them, of course, that's okay.
So that's not what I meant. I meant, can we just calculate the same thing by 1 minus
1 minus what?
1 minus those three probabilities?
නෑනේ දැන් මෙතන තියෙන එකක් මේ වෙනවා කියලා 1 minus වුණොත් එහෙම මේ මොකක්ද කියන්නේ ඒකෙන් විරුද්ධ වචනේ වෙන්නේ නැහැනේ මේ මෙතනදී මේක වැඩි කරොත් වෙන්නේ පළවෙනි එකත් conforming දෙවෙනි එකත් conforming තුන්වෙනි එකත් conforming කියන එක විතරයි. එතකොට ඒකේ විරුද්ධ එක නෙමෙයි එකක් conforming කියන දෙකක් conforming එකත් ඒකේ විරුද්ධ එකයි තියෙනවා තුන.
Then at least one back.
ඔව්. ඒක. මේ තුන වැඩි කරොත් වෙන්නේ first one is conforming and second one is conforming. That means all three are conforming කියන එකේ probability විතරයි ඒකෙන්. එතන අහලා තියෙන්නේ one back non conforming at least නෙමෙයි. At least වල නම් අරගෙන. Right, so we will come to calculate probabilities like this little later using the probability rules. So that's why we need event operations. In order to calculate probabilities like that and using those, we need probability rules. Actually, we looked at event operations earlier. Now we have to calculate probability rules. Look at probability rules. But before looking at probability rules, we have to discuss something called conditional probability rules. So before defining the conditional probability, just to get an idea, we look at some examples. It's the same previous example with the bonus scheme and type of employee. So let's look at the same problem that we had earlier. Right, type of employee, that is the, and then type of bonus scheme. But I am now asking a different question earlier. Okay, if the employee, you randomly select an employee, if the selected employee is a clerk, what is the probability that he or she has bonus scheme too? Right? Now one can ask like this. You randomly select an employee from this particular 960 people. One might ask, what is the probability that the employee is a clerk who has bonus scheme too? That is one question to ask. It's a clerk who has bonus scheme too. In that case, you are looking at this cell here. Both happening. The person has to be a clerk as well as he has type 2. So if you define the event to be, for example, being a clerk is one event, having a type 2 is another event, we are looking at the probability of the intersection of those two, that will be equal to 44 divided by 960. So that probability is actually a kind of a unconditional probability. Oh, you can talk and be like, that is considering the whole population. What is the probability that if you randomly select a person, what is the probability that the person is a laborer? What will be that probability? 630 divided by 960. Okay? So probability is calculated out of the whole 960. So that is also an unconditional probability. What is the probability that the person will have type 2 bonus scheme? That is 377 divided by 960. That is kind of unconditional probability, but we don't use the word unconditional there. We just say probability of that event. This question is little different. If you randomly select an employee, if the selected employee is a clerk, what is the probability that he has a bonus scheme too? Right. Now, conditioning on the fact that we know the person is a clerk, knowing that the person is a clerk, what is the probability that he has bonus scheme too? So now we are looking at only a subset of the previous. Right. Out of the clerk, knowing that he is a clerk, out of these, what is the probability that person has type 2? So now, not from the whole sample earlier that we had 960, we are now restricted to clerks only. So therefore, the probability that the person is has type 2 given or knowing that the person is a clerk is equal to 44 divided by 170. 44 divided. So that is called the conditional probability. Conditional probability that the person has type 2 given the person is a clerk. Right. Oh, if you ask what is the probability that the person has type 2 without telling anything else, that is unconditional probability. Probability that the person has type 2 is equal to 377 divided by 960. That is the unconditional. So that kind of probabilities are important for us to look at conditional probabilities. What is the probability that the person is a clerk? කිව්වොත් එතකොට ඒක unconditional. Just what is the probability that the person is a clerk? Clerk is 170 divided by 960. What is the probability that the person is a clerk with bonus scheme 2? කිව්වොත් ඒක මොකක්ද? What is the probability that the person is a clerk with bonus scheme 2? කිව්වොත් එහෙම 44 divided by 960, that is also unconditional probability. So we have to, some people have difficulty in understanding distinction between these three, right? Intersection එකේ probability එකයි conditional එකයි බොහෝ වෙලාවට පාට කරගන්න. So intersection is of the probability of an intersection is unconditional probability. so the number in the intersection divided by the total, grand total. Conditional, when you say conditional, given that the person is a clerk, we are looking at that group only. Right? So if you, for example, draw a graph A and B. So if you ask probability A intersection B in the classical sense, right? You cannot explain in the classical sense. It will be equal to number in this set divided by number in the sample space. So the probability, if you ask probability of say A given B is written like this. No, A given B. A vertical line given B means when you know that B has already happened, what is the probability happening A at the same time, right? So in that case, your sample space is now this part, given that B has happened. ඒක වෙලා කියලා දන්නකොට මේ ඒවා අනාලෝගය නෑනේ. ඒකෙන් A වෙන කොටස වෙන්නේ මේ ටික ආයසරයක් මේ ටිකේ සම්භාවිතතාවය. හැබැයි sample space එක මේකට. ඒතකොට එතන පොඩි adjustment එකක් කරන්න ඕනේ අර probability කියන එකට අර ලක්ෂණ ටික තෘප්ත වෙන්න ඕනේනේ. එකතු එක වෙන්න ඕනේ අනම්මන දින. ඒතකොට ඒ අනුව තමයි probability එක define වෙන්නේ. එතනදී අන්තිමට conditional probability also a type of probability. It also satisfies the Kolmogorov axioms. The conditional probability are always greater than 0. Always any conditional probability is between 0 and 1. Union එකට අතර කතාව conditional A rule එක එමුමයි තියෙන්නේ. ඒක එමුම. So that's the meaning of the conditional probability, right? Given that something has happened, so your sample space now reduces to that set. Within that, you are looking at the probability of occurring the second event B. Okay. මේක පොඩ්ඩක් අතහැරලා යමු. Make a condition. Just to understand further conditional probability, and then I'll come to the definition after that. Look at this. A box contains 3 white balls and 2 black balls. The 3 white balls have numbers 1, 2, 3 on them. So let's say W1, W2, W3 for example, right. 2 black balls have numbers 1 and 2 on them. B1, B2. A ball has been taken from the box. What is the probability that it has number 1 on it? If you take, so that probability, what is the probability that it has number 1 is actually
2
an unconditional probability, right? So that is equal to 2 divided by 5, 2 out of 5. If you have noticed that the ball taken from the box is white, what is the probability that it has number 1 on it? So that is a conditional probability. Given that it is white, what is the probability that it has number 1 on it? That is just 1 over 3. 1 over 3. Right. Okay. Then we got the box contains 3 white balls and 2 black balls. 2 balls are taken one after the other without replacement. 3 white balls, 2 black balls. 2 balls are taken. What is the probability? The second ball is black. මේක අපි දැන් කලින් කරානේ second ball එක black වීමේ සම්භාවිතය. ඒතර ඒක අපිට මොකද? එතන අහන්නේ මොකද්ද? එතන අහන්නේ just a unconditional probability. What is the probability that the second ball is black? Okay, next question. If the first ball is white, what is the probability that the second ball is black? Now, knowing that it is white, the first ball is white. Right? So, one ball is taken, one first is white. Now, we are taking from the remaining ball because we are taking without replacement. So, therefore, there are 2 white balls and 2 black balls in the box now when you take the second one. So, what is the probability that the second ball is black then? 2 out of 4. 2 out of 4. If the first ball is black, what is the probability that the second ball is black? If the first ball is black, then there are 3 and 1. So out of 1 out of 4. Right. So like that, in most of the situations, we can calculate or think about the conditional probability, like what happens, what is the situation after the event has occurred. Right? We don't need any formulas. But sometimes we have to use formulas to calculate these ones. So therefore we need the definition as well. Make him a with replacement of the together. Let's look at this one. So this is again a type of A-level problem. I just want to emphasize something here which is usually not emphasized in schools. Right. Usually this kind of problem people draw a tree diagram usually, so they mark something on the tree diagram, but most of the times they don't really explain what it is. Only let's see. In a certain shop sells 3 different brands of TV. 50% of its sales are brand A, 30% are brand B, and 20% are brand C. So then altogether 100%. Each manufacturer offers 1 year warranty. It is known that 25% brand A TVs require warranty repair work, whereas corresponding percentages brands B and C need 20% and 10% warranty work. So I have defined some events A, B, C. That A is the event that sold TVs brand A, B, and C. Similarly, and R is the event that a TV require warranty repair work during the warranty period. Right. So then මේ වගේ එක මට පෙන්නන්න ඕනේ දැන් මේකේ tree diagram එක අඳිනකොට කොහොමද අඳින්නේ? So any TV can be A, O, B, O, C. So usually people just write down the numbers on top of that, like say for example 50%, 20% and 30%, right? But it's better to write down probability of A. A is equal to 0.5, probability of B is equal to 0.3, probability of C is equal to 0.2. Right. And then any brand A TV may require warranty work or may not require warranty work. So you can just say R, O, R dash. R, O, R complement will happen. Here also R, O, R complement will happen. C, R, O, R complement will happen. So here also they just write down the numbers usually. What are the numbers? 25%, 20 and 10. Okay, so this is 0.25, 0.2 and 0.2. So they just write down like that, and therefore this is going to be 0.75, this is going to be 0.8, this is going to be 0.9. But what is this actually? What probability is that? Yeah, so that is actually a conditional probability, right? So this is not emphasized usually in schools. So this is actually the probability of R given A is equal to that. That is what it is. Probability of R given A, and this is the probability of R dash given A. That is 0.7. So, and similarly, this is the conditional probability of R given B, is the conditional probability of R dash given B. එහෙම නැත්නම් නිකන් ඔය මේ ඉස්කෝලේදී කරන්නේ මේක මේව අතර ඉතින් සම්මත කියලා මේ නිකන් ඔය වැඩි කර කර දාන්නේ වැඩි කරනවනේ මොනවද එන්නේ කියලා දන්නේ නැහැ. මේ රූල් එක ප්‍රොබිලිටි රූල් එකක් ඇප්ලයි වෙන්නේ. මේ රූල් එක මොකද්ද කියලා උගන්වනවා වෙනම. හැබැයි ඒක තමයි ඇප්ලයි වෙන්නේ කියලා ළමයි දන්නේ නැහැ. ඔය වැඩි කරනවා කියලා. එතන පොඩි ප්‍රශ්නයක් තියෙනවා ඉස්කෝලේ. So here if you draw the tree diagram, it's better to write down what it is actually, then students will know what they are in. So now I am coming to the definition of the conditional probability. Right? So this is how you define the conditional probability. Remember, as I told you that it has to be the intersection given B, for example. This is A. So we are looking at this quantity, but within this B. Right? So we have to now scale down the probability, but you cannot just take this probability. Right? You have to scale it out of the probability of B. That's why you have to divide it by probability of B. Earlier, when you had the unconditional probability, you had here probability of S out of the whole sample space. The probability of S is equal to 1. Right? So that's why you don't need anything like that. You just write down probability of. But now you have to scale it down so that these probabilities will have the properties given by the Kolmogorov equation, Kolmogorov axioms. Otherwise, it will not be a probability. So anyway, this is how you define the probability of event A given B. Of course, given B, in order to talk about the probability of A given B, B has to be able to occur, right? B event by now, so the probability of B cannot be 0. Mathematically also a probability of 0, B is equal to 0, this is undefined. So practically, in order to talk about given that B has occurred, the probability of B should be greater than 0. On the other hand, mathematically, in order to define it like this value, whatever that number has to be, not equal to 0. Right. මේකේ අපිට පුළුවන් මේ probability අර අපි කතා කරපු මේ ටික ඒකදී අපි we just looked at without any formula we calculated, right? පළවෙනි එක white none, දෙවෙනි එක black cream සම්බන්ධතාවය. By considering the situation at that point, you can get the same answers if you just apply the formulas, but that's not necessary in this case. But I just ask you to do that as a practice. You just look at it, calculate like this, right? You can use the formula. In that case, the probability of B given B intersection A and probability of A can be calculated using the classical method. So use the classical method and you see that the same answer. Right. So once you have this definition, conditional probability definition, we can now define the independence of two events. Independence. So to explain that, let's consider two situations. Say you have two events A and B. Suppose you are considering probability of B, that is the unconditional probability, and also you are considering the probability of B given A. You calculate the probability of B without knowing whether A has occurred or not. So that's this one, unconditional probability. You can calculate the probability of B when you know that A has occurred. That will be the probability of B given A. Right? Now, if whether B occurs or not depends on whether A has occurred or not, then what can you say about these two probabilities? B සිද්ධ වෙනවද නැද්ද කියන එක, A සිද්ධ වෙනවද නැද්ද කියන එක මත රඳා පවතිනවා නම් මේ සම්භාවිතතාවය දෙක සමාන වේද අසමාන වේද? They have to be different, right? මේකෙදි කියන්නේ A වෙලාද නැද්ද කියලා දන්නේ නැතුව කෙලින්ම probability of B හොයන එක. මෙතන තියෙන්නේ B වෙලා කියලා දන්න වෙලාවට probability of B හොයන එක. ඒකට A සිදුවීම හෝ නොවීම මත B රඳා පවතිනවා නම් මේ probability එක මේකට වඩා වෙනස් වෙනවා. අනිත් පැත්තට ඒකට එහෙනම් අපි කියනවා මේ දෙක වෙනස් නම් අපි කියනවා මොකද්ද? We say A and B are dependent events. Dependent. On the other hand, if these two are the same, then we say two events are independent. Right? If probability of B කියන එකයි මේකයි දෙකම සමාන නම් ඒ කියන්නේ මේක වෙලාද නැද්ද කියන එක මත රඳා පවතින්නේ නැහැ. Probability of B කියන එක. Independent. Doesn't depend on that. Independent. B doesn't depend on A. So in that case, this conditional probability and unconditional probability will be the same. So that's how you define the independence of two events mathematically. Two events are independent if and only if the conditional probability of one given the other is the same as the unconditional probability of the first. So that is the definition. So that gives you, so these two are equal if independent. This goes both ways, right? If this happens, we say A and B are independent. On the other way, if A and B are independent, then these are the same. Right? So what does it mean? Probability of B is the same as probability of B given A, but B given A, if you write down the definition, is equal to probability of A intersection B divided by probability of A. Right? That is coming from the definition. So this implies that. This implies probability of A intersection B is equal to probability of A times probability of B. So that is another way of saying, defining the independence of two events. A and B are independent if and only if the probability of the intersection is equal to the product of individual probabilities. And on the other hand, if they are, if this happens, then they are independent. So that is kind of one probability rule coming from the definition of the independence. If A and B are independent, the probability of happening both at the same time is equal to the product of individual probabilities. It's coming from the conditional probability definition, and the meaning that if one is independent of the other one, unconditional probability and conditional probability should be the same. Right. So you can check actually once you can calculate the conditional probability and unconditional probability. If they are the same, then they will be two events will be independent. Otherwise, they will not be independent. That means dependent. So I will just leave that for you to do. So now, including that, we will talk about general probability rules. These are the ones that we have to use always when you want to calculate the probability of some complex event, when you know the probability of some simpler events. Okay, so there are not many rules actually, very few rules. The first one is, we have already used that, that's called the complement rule. Right? So if you know the probability of some event E, you can get the probability of the complement by just 1 minus the probability of E. That is because the probability of, okay, it's coming from the second rule actually. Because, okay, let's look at the addition rule. Addition rule means generally this one. Probability of the union, probability of A union B is equal to probability of A plus probability of B minus the probability of the intersection. But we have already discussed about the mutually exclusive events earlier, right? When you talk about the union, sorry, the intersection. If the two events cannot occur at the same time, that means if the probability of the intersection is equal to 0, or you can say the intersection is equal to the intercept. That happens if the two, then we say they are mutually exclusive. Events are mutually exclusive. So if A and B are mutually exclusive, then this part will be 0. So So therefore, probability of the union will be equal to just the sum, right? So that's why you saw earlier in when you write down some of the things you have to add and some things you have to multiply. So product rule and addition rule, both that can have to apply there. Let's look at that one a little later. Right? So this is a special case therefore of this general addition rule. Probability of A intersection union B is equal to probability of A plus probability of B if A and B are mutually exclusive or if they cannot occur at the same time. So from that actually this comes, for example, you can say the sample space is equal to E union E dash. So the probability of S is equal to probability of this, but these two are mutually exclusive, therefore the probability is equal to probability of E plus probability of E dash, and we know this is equal to 1 from by the axiom, so therefore that one comes directly from the axiom and this rule here. And the multiplication rule is just the one that I just mentioned. Probability of A intersection B is generally equal to this O that's coming from again the definition, because in general probability of A given B is equal to probability of, I am used to write down PR, A intersection B divided by probability of B. So cross multiplication gives you this formula. That's the general multiplication rule. Right? Probability of A intersection B is equal to probability of A given B times probability of B, or the same thing you can write down. Probability of B given A times probability of A. Right? So which formula you use, whether you use this formula or this formula, depends on how you have defined your events and which one is easy to find. For example, make a define right. So the special case is if A and B are independent, then this one will be equal to probability of A. So therefore the probability of intersection is equal to probability of A times probability of B. And similarly, if A and B are independent, this probability will be equal to probability of B. In that case, again it will be equal to probability of B times probability. Okay, so those are the main ones. Right. Now let's apply those three rules and get this simple probability. Two pumps are connected serially, fail independently of one another on any given day. The probability that the older pump fail on any given day is 0.05. The probability that the newer pump fail on any given day is 0.01. The system fails if at least one pump fails. What is the probability that the pumping system will fail on any given day? So this is simple, but we have to apply the rules because we are given the probability of some events and we have to find out the probability of another event, which can be written in terms of these events of which we know the probabilities. Anyway, first let me ask a different question. Now, here you are given some probability. What kind of probability, or do you think how that probability was decided? How do you think that was decided?
Relative frequency.
Yeah, that is actually not a real probability. That must be again an approximate probability, right? Based on previous data, right? It's a relative frequency probability obtained using the previous data, right? So that means out of, say, for example, large number of days, how many days it was failed. So depending on that, they have decided. So somehow they have got those numbers now. So here you have a situation. Serially means like this, no? So old pump, new pump. Right. So suppose these are probably water pumps. So therefore, if at least one of them fails, then water doesn't go out, no? Water comes in. Right? So we know the probability that this will fail it on any given day is 0.05. The probability that this one fails is 0.01. What is the probability that the system will fail on any given day? So how do you, first of all, you have to define the event that the system fails in terms of two events. So let me define some events. First of all, let's say this is old. Old means old pump fails. Let's take N to be the event that the new pump fails. So we are given the probability of those. We know probability of O is equal to 0.05. Probability of N is equal to 0.01. We know those two things. Now we have to define the event that the system will fail. So let's say S is the event that the system fails. So somehow we have to define S in terms of O and N and then use the probability rules. So how do we write down S in terms of O and N? System fails means?
O intersection in union in intersection. Sorry, O intersection in dash union. O dash intersection in union. O intersection.
Yeah, you can say only the first one, old one fails, this one works. O, only this one fails and this one works. O both fails, right? So therefore you can write down S as O intersection N dash union O dash intersection N union O dash and O and N both fail. I'm taking O to be failing. Right. So S system fails can happen this way, O this way, O this way. So therefore we have to find out the probability of S. So probability of S is equal to probability of this whole thing. So how do we apply the rules now? So if I say this is, for example, A, B, C, probability of S is equal to probability of A union B union C. So what type of events are ABC? Yeah, ABC are mutually exclusive, right? If A happens, these two doesn't happen at the same time. If B happens, then these two happen at the same time. So therefore, according to the probability laws, this should be equal to probability of A plus probability of B plus probability of C. The special case of the addition rule. Now we have to find out the probability of individuals. So probability of A is the same as probability of O intersection N. Right. So O and N are N dash. Yes. Thank you. O and N dash. Right. So O and N are independent. Right. We stress whether they fail independently. Right. Whether one fails or not doesn't depend on whether the other fails. Right. So then if O and N are independent, we can prove that O dash and N dash are independent, O and N dash are independent. Practically also we can think about like that. Mathematically also we can prove that. So therefore this should be equal to probability of O times probability of N dash. Again the special case of the multiplication. So probability of O is equal to 0.05. Probability of N dash is equal to 1 minus 0.01. So similarly you can find out these ones. So that's the application of the first of all event operations right? You write down one event in terms of the other events and then apply probability rules. Okay, let's look at a circuit. Suppose you have connected 3 bulbs or something.
So use these instead. That's hard. Yes.
Okay. So 3 components are connected to form a system as shown in the figure. Probability that any component works is 0.9. Calculate the probability that the system works. So the probability that this component works is 0.9. This works individually. Right? Works is 0.9. This works. The probability that it works is 0.9. Separately below and connect like that. So what is the probability that the system works? So again we know the probability that the first one works. So you can define some event. For example, say W1 is the event that the first component works. Then we know the probability of that is equal to 0.9. Let's say W2 is the event that the second component works. So the probability of that is also 0.9. Say W3 is the event that the third component works. Then the probability of that is also 0.9. We know those. So let's define again by S the event that the system works. So, because only we know the probability of W1, W2, W3, we have to write down S in terms of W1, W2, W3 and then apply the probability rules. So, how can we write down S? System works. There are a large number of ways you can write it, but let's go for the minimal way, right? This must work, no? Suppose current or whatever goes like that. So first of all, this must work. Then all this must work. So therefore, S can be written as W1 and W2 or W3. W1 must work, and then this system should work definitely, but that is working if this or this or both. So therefore the probability of S is equal to probability of this whole thing. So in order to answer that, now we have to identify. So each component works independently, and therefore whether this part works or not doesn't depend on whether this one works. So therefore this and this can be considered as mutually exclusive parts. So this is, for example, A and B. A and B are mutually exclusive. Therefore the probability first we can write down as probability of W1 plus probability of W2 union W3. That is the addition rule, special case.
That's for union, no? That's intersects multiplication.
තව මම මේකට එළිය දෙන්න මේකට ඇප්ලයි කරා මේකට ඇප්ලයි කරා මේක මේ කියන්න ඕනේ තුන් යහපත කරා මොකද ප්‍රශ්න
So intersection they
sorry intersection නෑ we
intersection is
මට වැරදුනේ නේද
yeah.
independence එක අපිට ගන්න intersection එක තිබුණා අපිට බලගන්න වෙන්නේ union එක නෙවෙයිනේ මේ independence එකක්ද කියලා බලන්න. ඒකට ඇත්තටම independent වෙනවනේ මෙතන නේ. mutual exclusive වෙන්නේ නැහැ ඇත්තට. මොකද මේක වැඩ කරන්නේ නැති වෙලාවට මේක ගන්න බලක් තියෙන්න පුළුවන්. mutual exclusive නෙමෙයි. yeah thank you. නමුත් මේක වැඩ කරනවද නැද්ද මත මේක වැඩ කරනවද නැද්ද නදාපොත. මේක වැඩ කරන වෙලාවට මේක වැඩ කරන්න පුළුවන් නැති වෙන්න පුළුවන්. මේක වැඩ කරන වෙලාවට මේක නැති වෙන්න පුළුවන්. independence තමයි එන්නේ. So then so therefore this should be correct like that. Multiplication. Sorry about it. And now, okay. W2 union W3 coming from the general addition rule, right? So this part can be written as probability W2 plus probability W3 minus probability of W2 intersection W3. That's the general addition rule. Because we cannot take them to be mutually exclusive. W2 වැඩ කරන වෙලාවට අනික අනිවාර්යයෙන්ම වැඩ කරන්නේ නැහැ කියලා නේ. වැඩ කරන්න බෑ කියලා නේ. ඒක වැඩ ගන්න පුළුවන්. ඒ නිසා they are not mutually exclusive. Exclusive වුණාම මේ වෙලින් කරලා ගන්න දෙනවා මේක අතයි. But here is not a general situation. So they are right now this can be obtained by knowing that W2 and W3 are independent. They are independent. So ඒ නිසා ඒක මේක කියන්න පුළුවන්. Make as a probability W2 times probability of W. So it's going to be this probability times this whole probability where it is as a probability W2 plus probability W3 minus the product of those two. So like that. So one might ask, okay, suppose you have 5 systems like this. This is the probability that one system works. Suppose you select 5 randomly, 5 systems like this. What is the probability that 2 of them will work? And this kind of questions can be asked. We will answer that kind of questions later. Let's see whether we can answer this question. It is known that approximately 2% of the products produced in a certain production line are defective. 2% are defective. 3 products are taken randomly, one after the other. From a production line, what is the taken from the production line? What is the probability that 2 of them are defective? So we know that probability any item will be defective with 0.02 probability. 3 products are taken randomly, one after the other. Right. What is the probability that 2 of them are defective? Right. So how do we answer this question? Again, we have to somehow define some events of which we know the probability. And then we have to write down the event of interest in terms of those. Right. How can we do that? I'll define some events. For example, I say D1. They got clear the entire what is the chance? That was very good. And the first one.
There are 3 more here.
Defective. Right. Let's say D1 is the event and the first one is defective.
Try to middle.
Chance is 1 Oh, I don't know whether the others are also the same. මම හිතන්නේ වෙලා තියෙන පෑන් නෙමෙයි දැන් තියෙන ප්‍රශ්නේ බෝඩ් එකේ. බෝඩ් එකේ කුණු එකතු වෙලා ඒක උඩ දිය කොහොම ටිසුන් දෙකක් ටිකක් මේක ටිකක් වෙයි. Alright, so D2 the second item, the second product is defective. Let's say D3 is the event that the third product is defective. If you define like that, we know the probability of D1 is equal to 0.02, probability of D2 is also 0.02, probability of D3 is also 0.02. D1, D2, D3 are what kind of events? They are independent. Whether the first one is defective or not doesn't depend on usually. It is coming from a large production process, therefore In that case, we can take it to be dependent. So, the question, what is the probability that two of them, when you take three, two of them are defective, right? So let's say, for example, E, in the event that two products are defective. So how can we write down E in terms of D1, D2, D3? E is equal to, you can say, for example, D1 intersection D2 intersection D3 dash. That is one way. First one is defective and second one is defective and third one is defective, non-defective. O, first one is defective and the second one is non-defective and the third one is defective. O, first one is non-defective and the second one is defective and the third one is defective. That is the only way, right? So we want to find out the probability of E, that is the probability of, so if you call this, for example, A, B, Z, probability of E is equal to probability of what? Probability of A union B union C. But A, B, C are mutually exclusive, right? මේක වෙනවා නම් යම් කිසි අවස්ථාවක ඒ වෙලාවෙම මේ දෙක මේක වෙලා තියෙනවා. මෙතන D1 defective, D2 defective, D3 non-defective. ඒ වෙලාවෙම මේක වෙලා තියෙනවා. මේ විදිහට is mutually exclusive. Therefore, by the special case of the addition rule, this is equal to probability of A plus probability of B plus probability of C. Right? So, if you consider, for example, probability of A is equal to probability of D1 intersection D2 intersection D3 dash. Now, D1, D2, D3 dash are independent, right? Because whether one is defective or not doesn't depend on whether the other ones are dependent. So therefore, using the special case of product rule, this will be equal to extension. We just defined it for only two events, but it can be extended for more than two events. So that is equal to probability of D1 times probability of D2 times probability of D3 dash, which is equal to 0.02 times 0.02 times probability of 98. So similarly other ones can be found, and therefore the total probability of E can be found. So that's how you apply the probability rule. Okay. Now we are coming to the last two probability rules. This one is called the total probability rule. This is applied, you are interested in one event. You know several ways of happening that in conjunction with some other events. Or you know, you want the unconditional probability of some event, but you know the conditional probability of the same event given some event has happened. In that kind of situation, you use this law rule, probability, total probability law, to find out the unconditional probability. You want some unconditional probability of event B, but you know the probability of B given some events A1, A2, A3 and so on. So if those A1 up to A are mutually exclusive and exhaustive, this theorem can be applied. They have to be mutually exclusive and exhaustive. Exclusive means there is no intersection among A1 up to N in this case, N events. Exhaustive means the union of those has to be equal to the sample space. So that means we know some conditional probabilities where the conditional events actually made up of the whole possibility. So in that case, we can very simply write down probability of B is equal to probability of B according to this picture is equal to B intersection A1. Okay, first of all, you can write say B is equal to B intersection A1 union B intersection A2 union B intersection A3 union B intersection A. Right? Generally, it's like that. Some of them may be empty. For example, A1 intersection B is empty, but generally, when you have this kind of situation, generally you can write down like this. B is equal to the union of intersections with these things. So because A1 up to An are mutually exclusive, these are also mutually exclusive. So therefore the probability of B is equal to probability of this plus probability of this plus probability of this plus probability of this. Because these are mutually exclusive. Now we can write down all these intersection probabilities. Probability of B intersection A1 can be written as probability of B given A1 times probability of A1 from the definition of the conditional probability, right? Because conditional probability of B given A1 is equal to probability of B intersection A1 divided by probability of A1. So when you take the cross product, you get probability of B intersection A1 is equal to conditional probability times this one. Right? So similarly, you can write down all the intersection probabilities in terms of conditional probabilities to get this. That's what the total probability law is. So you need to know the probability of individual A1 up to An probabilities which are mutually exclusive and exhaustive events. In addition to that, you have to know the conditional probability of B given each A1 up to An. Then you can apply total probability law to find out the probability of B. So you apply this theorem usually this kind of situations where you have several possibilities and then conditioning on those there are some other possibilities. So in order to find out the probability at some n place, then you can apply this, right? If you look at the same previous problem, so a TV can be a brand A or B or C. These can be required repair warranty or not requiring repair warranty. So unconditional probabilities are given. These are given here. 0.5, 0.3 and 0.2, and then conditional probabilities are also given. Probability are given A is equal to 0.25. Probability of given B is 20. Even C is 0.1, therefore you can find out these ones. Right. So if you want to find out probability of R, for example, then you can use probability of R dash. what is the probability that the random selected TV sold by this shop will require warranty repair? Right? So the probability of R is like B, because this is a situation where you have three mutually exclusive and exhaustive events. A, B, C are mutually exclusive and exhaustive. R is some other event. So you can write down, use the condition of probability. The total probability law. Probability of R given A times probability of A plus probability of R given B times probability of B plus probability of R given C times probability of C. All of them are known, therefore easy to find out the probability of R. Right, so the last one, Bayes theorem. So we use Bayes theorem when you know the same situation, same condition have to happen. Right? There should be some A1 up to A mutually exclusive and exhaustive events. B is any other event in the same sample space. Right? So if you know the probability of B given A1, probability of B given A2, probability of B given A3, when you know those things, if you want to find out the condition of probability the other way around, reverse, right? If you want to find out what is the probability of A1 given B, right? Probability of A2 given B, right? So that's the reverse of what you know. Then you apply the Bayes theorem. So the same situation, but now you need, for example, probability of say A1 given B. I can be 1 up to any value. Right? So by definition, this is equal to probability of A1 intersection B divided by probability of B. That is the definition of the condition of probability. And this intersection part we can write down using the conditional probability, using the multiplication rule, so that we can write down probability B given A1 times probability of A1, that part, and then the probability of B. So the probability of B coming from the total probability law in the previous theorem. So that is what this part is. Probability of AI multiplied. Probability of AI. So that's what it is generally. Okay. Ewa mama idani karane aiko komati wala. Nege puluhan yang ulan karane. Simple. Right. तो मौलिक probability क्या नहीं होता? Waiting. Then यहाँ पे तो we will discuss next day. Using some models called binomial model. I don't know Poisson model is in the book, but I will look at it. Right. So some models. Any questions so far? So this is where the A-level probability ends. Bayes theorem. So whenever you want to talk about the modeling, usually we have to define something called random variables, and then modeling goes on random variables. Here all these things we were looking at events as subsets of the sample space. So, in order to write down events in terms of the random variables and assume some distribution for random variables, we can discuss next time.
We